When you've completed this lesson, you should be able to simplify expressions that have powers and roots in them and solve for a variable in an equation that has powers and roots. Photonics technicians need to work with powers and roots quite a bit. For example, powers of like 6 to the 3 power, 2.7 to the 5 power, or with variables such as x squared or 2x plus 5 to the 7th power. Or you may have roots such as the square root of 2, or with variables the square root of x over 3, or cube roots like the cube root of 6 and the cube root of an expression in an equation like 5z squared plus 3z minus 12. Sometimes you'll have a formula like radiation intensity. I is a function of the distance from the source. I is equal to I sub 0 over d squared. Or you may have a more complicated expression like the threshold gain in a stable laser cavity is given by G sub A is equal to 1 divided by the square root of R sub 1, R sub 2 times L. Let's look at a typical scenario that a photonics technician might need to solve. A measure of the difference in time required to propagate light down an optical fiber is called the intermodal dispersion, tau sub I. And that's equal to L divided by 2n1c times the numerical aperture squared. And the numerical aperture is square root of n1 squared minus n2 squared. And you're asked to find out what is the intermodal dispersion for a 1 kilometer fiber with two values of n1 and n2 given there and using the speed of light. And we'll come back to that after we've reviewed some of the skills necessary to solve that problem. Powers are just repeated multiplications. So power notation is a shorthand way to write repeated multiplications. You might recall the powers of 10 you saw in the scientific notation module. For example, 10 squared is equal to 10 times 10, and 10 cubed is equal to 10 times 10 times 10. So we just repeated the multiplications of 10 based on those exponents. Well, similarly, we could have the expression 8 to the 4th. That's a power. The 4 is the exponent, and 8 is known as the base. The base is used as a factor exponent times. That is, 8 is multiplied by itself 4 times. Or we can say that we have 4 factors of 8. A number or a variable with no power is the same as the first power. So we'll say 5 is the same as 5 to the 1 power. 10 is the same as 10 to the 1 power. A is the same as A to the 1 power. X is the same as X to the 1 power. So anytime you see those variables by themselves, know that they really have a 1 as an exponent to them. That'll become important when you start multiplying and dividing powers. A number raised to the 2 power, we say, is squared, right? So we have 6 squared or x squared. A number raised to the 3rd power is commonly said to be cubed, and so we'll have 4 cubed or y cubed. And a number raised to the 4th power, it would be like 7 to the 4th, and we'd say z to the 4th power. Let's look at the example 1 that discusses braking distance with the formula B is equal to r squared divided by 30f. B is the braking distance, r is the initial speed, and f is the surface factor that you're driving on, and given by this table of values here. So, given that a car is traveling at 55 miles per hour on dry asphalt, let's find the estimate of the car's braking distance. Well, the solution is just simply to substitute the values into the formula. The units are already prepared in the driving surface factor to yield the braking distance in feet if we supply the initial speed in miles per hour. So if we put our speed of 55 miles per hour and our driving surface factor for the asphalt road is 0.85, then multiply it times 30 and evaluate that. We'll end up with 120 feet is the braking distance. Part B says we've got some skid marks on wet asphalt at an accident scene that measured 215 feet. So what would be the initial speed of the car that caused those skid marks if they were braking as hard as they could? Well, first, we need to isolate R in the formula because we're trying to find out what it was the rate of this car. So we'll multiply both sides by 30F because R is divided by 30F. And the 30F on this side will cancel. On the other side we'll be left with now R squared is equal to 30F times B. Take the square root of both sides so that we can get R by itself. The square root of R squared is equal to R, and the square root of 30FB is on the right hand side. So there's our answer to the formula for R. Now we just need to substitute the values into the formula, remembering we're using F equals 0.65 for wet asphalt. And we have R is equal to 30 times 0.65 times 215 and the square root of all of that, which you evaluate with your calculator and you'll come out with 65 miles per hour. Now, multiplying positive numbers always yields positive values. However, if we have negative numbers now, multiplying an even quantity of negative numbers will yield a positive value. So if we multiply -5 times -5, that's -5 squared, we'll get 25, a positive number. If we multiply an odd quantity of negative numbers, we'll get a negative value. So if we have 3, 5, 7, 9, odd numbers of factors that are negative, we'll get a negative number. So if we have -5 cubed, where -5 is now a factor 3 times, then the result will be -125. So in general, we can summarize the results of our odd and even powers in this table. If we have an odd power in a positive base, we have positive value. If we have a negative base, we'll have a negative value. But in an even power, no matter what we have, positive or negative base, we'll always have a positive value. You might want to jot this table down. This will be helpful to remember. Now there's a trap you have to watch out for when you're using your calculator. Okay, you know that 5 to the 4th is going to be positive 625, right? And -5 to the 4th will also be 625, positive 625. But try this with most calculators, -5 to the 4th power, and you'll get an answer of -625. Oh, what happened? Well, do you remember the "please excuse my dear Aunt Sally"? Well, the calculator knows that rule and it follows it, and it first evaluates the exponent in the 5 to the 4 and then multiplies by -1. So the result is -625, not what you expected. So the moral of your story here is know your calculator. All right, you've heard of square root, right? The square root of 49 is the value that when squared that yields 49. And we found out that 7 would do that. 7 squared, sure enough, equals 49. So the square root of 49 equals 7. Similarly, the cube root function. The cube root of 125 is the value that when cubed yields 125. So 5 cubed equals 125, and so the cube root of 125 equals 5. So in general, we can say the nth root of a number x, or shown like this, is that value when raised to the nth power that yields the number x. So if we have r to the n equals x, then we can say with confidence that the nth root of x equals r. Now, most calculators have a square root key or an inverse function used with the x squared key. So for example, let's find the square root of 256. The solution is going to vary by the type of calculator you have. With a TI-80 series of calculator, you will take the second square root function that's on your key and enter then 256 and press enter, and you'll have your result. With an earlier model of TI-30 series, you will have to enter 256 first and then go for the second square root function and then press equals, and you'll get your result. And of course the answer is 16 will appear in your display in either case. And you can check your answers, and you should do this to be sure you're getting the right result that you expect. Remember, know your calculator, by simply calculating 16 squared. Do you get 256? Now let's look at example 3, where we're given a square storeroom floor must provide 6,000 square feet of storage space. What should be the size of this storeroom? How long do the sides have to be? Well, the solution is to start off with the formula for this area of a square, which we know is A is equal to S squared, where S is the side that we're looking for then, right? So we're going to solve for S. To do that, we'll take the square root of both sides. Do you remember in an earlier module we talked about doing the same thing to both sides of an equation will yield valid results. So we're going to take the square root of both sides, and knowing that the square root of S squared is going to give us S. And so we have S equals the square root of A. Next we substitute for A our value, which is 6,000, into our calculator and evaluate that. The square root of 6,000 feet squared will separate out the units and the value. The square root of 6,000 we can do with our calculator, and the square root of feet squared will be feet. And so our answer is S is equal to 77.46 feet. Now does that sound right? To check it out, take your value for 77.46 and square it, and do you get about 6,000 feet squared? Cube roots now. Those are a little bit different. You may not have used those very often, and they're a little harder to work with on your calculator. Recall that the cube root of 125 is the value when cubed that yields 125. Just like we did with squared. 5 cubed equals 125, and so the cube root of 125 equals 5. Most scientific calculators have a root key on them, like x root of y, or an inverse function that will be used with the y to the x key. The undo operation for y to the x would be the x root of y. For example, let's find the cube root of 8 and see if we know how to do that. Well, it's going to vary by the type of calculator you have. Again, with the TI-80 series, you'll have to press the math button. Then you'll see the cube root function is on there. Then you enter your number 8 and then press enter at this point, and the calculator will give you the result. On a TI-30 series of calculator, you have to enter the value first, then press the second x root of y function, and then enter 3. So that tells that you want the third root, and then press equals, and you'll get your result. The answer 2 should appear in your display in either case. You can check your answer by calculating 2 to the third power, 2 cubed. Example 5 asks you to calculate the length of each side of a box. It must hold 256 cubic inches of material. It's a cube-shaped box, so that gives us a clue that the formula for volume of a cube is V is equal to S cubed. And we're looking for S, and so we're going to have to use some algebra to solve for S. We'll start by taking the cube root of both sides, remembering that the cube root will cancel the cube. So we'll be left with just S is equal to the cube root of V. We'll substitute in our value for V, 256 cubic inches, and then evaluate the cube root and the units separately. So the cube root of 256 and the cube root of the inches cubed gives us 6.35 inches. Now check your answer. If we take 6.35 and cube it, do we get about 256 inches cubed? Now let's look at the solution to that opening scenario with those complicated expressions. where we're asked for the intermodal dispersion using these two formulas. Notice that NA will have to be inserted into the formula here. Let's substitute in the given values. We have T is equal to 1,000 divided by 2 divided by 1.465 divided by 3 times 10 to the 8th meters per second, all multiplied by this expression for NA squared. Notice that the squares are going to cancel the square root for us. That's going to be very nice because now we can just simply take that expression and stick it into the numerator without having to do the root anymore. Remember, please excuse my dear Aunt Sally, because we're going to have to use that to evaluate this expression. And the result becomes 4.97 times 10 to the negative 8 seconds. More commonly, we'll be thinking of looking for nanoseconds, or 10 to the minus 9th seconds, so we might express that as 49.7 nanoseconds, or about 50 nanoseconds is the intermodal dispersion for this length of fiber. All right, now let's look at our practice exercises in this module. As always, we'll not do all of the exercises. We'll just do a few of them to give you a flavor for how to proceed on your own, and this will be enough to give you some confidence. Starting off with exercise 1, we have the period of a pendulum is given by T is equal to 2 pi the square root of L over G. And we're going to use G as 980 centimeters per second squared in this problem. What is the period T for a length of 25 centimeters? Well, we need to substitute the values in. T is equal to 2 pi times square root of 25 centimeters divided by 980 centimeters per second squared. And we'll handle the units separately. They're under the square root also. So the centimeters will cancel, and the per second squared will turn into just a second by itself. And the value of square root of 25.0 divided by 980 will have to be square root and then multiply by 2 pi. The result should be 1.004 seconds, and we've rounded that off. So a 25 centimeter pendulum has a period of slightly more than a second. Now if we continue on, suppose the length were shortened to 24.9 centimeters. Would the period be closer to 1 second? Well, we'll substitute those values in and find out. So we substitute 24.9 centimeters in, handle the units separately as we did before, evaluate the expression under the square root, and multiply by 2 pi. And we have T is equal to 1.002 seconds. So sure enough, shortening the pendulum by 1/10 of a centimeter brought the period a little bit closer to 1.00 seconds. Well, here's an extra challenge for you. We could just solve that formula for L and find the length of the period that has exactly 1 second, or exactly 2 seconds. I'll let you do that on your own using your algebra skills that you've developed in the last couple modules. Now exercise 2 gives us a problem of finding the monthly payment for financing a $2,600 car over 24 months using this formula here, that R is equal to P times I over 1 minus 1 plus I to the negative n power. Whew, how would you like to solve that problem? Well, we can start off by substituting the values in to find the monthly payment. Substitute 2,600 times 0.01 for the interest. 1% is the same as 0.01. And then also in the numerator, 1 plus 0.01 to the negative 24, since we want 24 months. We need to evaluate this with all the decimal places we can get in our calculator because it's a very small little number. So we're going to start by doing the 1 plus 0.01 to the negative 24, and we end up with 0.787566, and evaluate that expression in parentheses and multiply by 2,600. Okay, to do that with the scientific calculator, with the TI-80 series, for example, we have multiplied 2,600 times 0.01 divided by, now we need the denominator, and I'm going to do the math in my head for what's in the parentheses and call that 1 plus 0.01 is really 1.01. And we need to raise that to the negative 24 power. So notice we're using the power function and the negative operation function and close it all with the parentheses and press enter. On a TI-30 series, it's a little bit different. Well, again, we'll use 1.01 in our head that we'll add those two numbers. And then we'll use the Y to the X key and tell it what we want the X to be. We want it to be 24, and we want to change the sign to the negative, and then press equals. In both cases, we should get R is equal to about $122.39 per month. Exercise 5 gives us a formula for calculating the energy from a black body or a black object. It's radiating total energy R at a temperature T in Celsius. What's the total energy radiated then from a 300 degrees Celsius object? Well, we substitute the values for T and evaluate. So we put the 300 into the formula, and now we have to add these two things and take them to the fourth power. So here's the value to the fourth power, and here are the units all pulled out. We'll notice that we'll have c to the fourth here, and c to the fourth will cancel. And then we've got the numbers, scientific notation, multiplied times 573 raised to the fourth power. That's going to be a big number. Using a scientific calculator, again, we've got this scientific notation, 5.67 times to the EE negative 12 times 573 raised to the fourth power, and then press enter. For a TI-30 series, similarly, we have to do the exponent, the scientific notation, times 573 and y to the x to the fourth, and the result will be R is equal to 0.611, and we're left with just watts per square centimeter as the units. Second part of exercise 5 asks us to do the same thing with a 37 degree Celsius object. So again, we'll substitute those values in. The 37C goes right in where the T used to be, and that's going to all be raised to the fourth power, so we'll have 310 raised to the fourth power, and again the Celsius units cancel nicely. And using a scientific calculator as before, negative 12 on the exponent, not a subtraction, 12, and the power raised to the fourth. And on a TI-30 series calculator, similarly, using the y to the x key, will give us that R is equal to 0.052 watts per centimeter squared. Much less energy than the other one. Stirling's formula is a popular way to approximate the factorial function for very large numbers. You'll notice that n factorial is approximated by the square root of 2 pi n times n over e, the natural logarithm base, raised to the n power. That's a pretty complicated formula, but it's a lot easier than calculating n factorial with a large number like 30. Substitute n into the formula. So 30 factorial is approximately equal to the square root of 2 pi 30 times 30 over 2.71828 raised to the 30th power. When you use your calculator, be sure to use all the digits you can possibly get, because if you just use 2.718, for example, your answers will be way, way off when you raise something to the 30 power. So you'll have numbers something like this. The square root of 2 pi 30 is about 13.729. In your calculator, you'll keep all of those digits. And 30 divided by 2.71828, etc., is about 11.036. And again, you'll keep all the digits and raise that to the 30th power. And with the scientific calculators, with the TI-80 series, you'll do something like this, using the power function to the 30 power, like before. And similarly, you'll use the second e to the x to get your e here, and the y to the x function to get to 30 power. And the result should be about 2.6452 times 10 to the 32 power. Wow, that's a big number. All right, so I hope that you've gotten your confidence built up now by going through this module with me and working some of those practice exercises so that you can work out the rest of those practice exercises yourself. We'll see you again next time.